So let's finish the material from sets and then go ahead and discuss a little bit about functions. So power set. The power set of a set A is defined to be as a set consisting of all subsets of A. Set of all x's with the property x subset of A. Very important to know that empty set is always an element of the power set. So note, empty set is a subset of any set or any set A. How to prove this? Well, simply use the definition of the subset. So to prove that empty set is including subset of A, we have to prove that for every x is in empty implies x is in A. But in this implication, the first item here is false, because that's what empty set is. It has nothing in. It's an empty set. So because this is false, the full implication is true. The only possibility for implication to be false is false would imply, if it would be true, it would imply false. So truth leads only to truth. Truth can never imply false. But false can imply everything, including truth. So empty set is a subset of every set. And therefore, empty set belongs to the power set. Let's take some examples. Example 1, power set of, let's say, 1, 2, 3. Is a set consisting of always empty set. Empty set belongs to the power set. Then let's list subsets with one element. So subset 1, subset 2, subset 3. Then subset 1, 2, subset 1, 3, subset 2, 3. And then, so we are done with the subsets, all subsets with 2 elements, and keep moving. Subset with 3 elements is only 1. Subset consists of 1, 2, 3. With the only subset with 3 elements of the full set 1, 2, 3. Then close the set. So, how many elements we see in this power set? 1, 2, 3, 4, 5, 6, 7, 8 elements. And this is kind of natural because for the set 1, 2, 3, every subset of 1, 2, 3 can be uniquely represented by a bit string with of length 3. So, how many bit strings of length 3 are there? So we can have like in a truth table, right? So we can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. For every bit string out of those 8 bit strings, it corresponds to a subset. So this corresponds to the empty set. This corresponds to a set consisting of subset consisting of 3. This corresponds to a subset consisting of 2. This corresponds to a subset consisting of 2 and 3. This is a subset consisting of 1. This is a subset consisting of 1 and 3. This is a subset consisting of 1 and 2. And finally, there is a subset 1, 2, 3. So, what's obvious at this moment, the number of elements in the power set equals to 2 to the power the number of elements of A, because there are exactly 2 to the power n bit strings of length n. So, any subset of A, if A has n elements, can be represented by a bit string of length n. Okay, let's take another one. Exercise 2. Let's look at the lower end of the set. So this is empty set. Let's find the power set of the empty set. So let's see, what is this? All the subsets of the empty set. Only empty set is a subset of the empty set. So let's open up set space and let's list all the subsets of the empty set. For empty set alone. Let's continue this process. So let's see power set of the empty set. So power set of the preceding set, power set of the empty set. Is the power set of the set considered the empty set. And this will be, let's open a set space. What do we put in here? Which are all the subsets of the set consisting of the empty set? Well, like I said, empty set is a subset of any set. So we are done with the subsets of the set consisting of the empty set with 0 elements. Let's move on to subsets with 1 element, which is the set itself. Then we are done. So like I said, power set of the empty set has 1 element. Power set of a set with 1 element is 2 elements, which we can see here. Can we do one more time? Power set of the power set of the power set of the empty set. 1, 2, 3. So there's the power set of the preceding set, set consisting of the empty set, and the set consisting of the empty set. Those the parameters. To avoid dizziness, so let's try to, in our mind, we can imagine, look at this like an A, and this like a B. So it could just be power set of the set consisting of A and B. So what would be the power set of the set consisting of A and B? Empty set, set consisting of A, set consisting of B, and the set consisting of A and B. So let's try to write them down. Empty set consisting of A, set consisting of B, and set consisting of A and B. Close the big set. So again, the power set of a set with 2 elements here is a set with 4 elements in this district. Okay, so in principle we are done with power set. That is at the elementary end of the spectrum. Next, let's do product of sets. Product, as in Cartesian product. A cross B, product of two sets, is a set consisting of all possible ordered pairs. Ordered pairs, A, B, small b, vertical bar, so with the property, small a belongs to the set big A, and small b belongs to big B. So we can imagine A like a set of x coordinates, and B is like a set of the theoretical y coordinates, and then we have to list all possible points with x coordinates in A and y coordinates in B. For example, 1, 2, 3, 1, 2, 3, cross 3, 4. So this is the set of x's, and this is the set of y's. So let's try to open a set space. What do we put in it? All possible points with x coordinate here and y coordinate here. So try to find all possible couplings between a point in here and a point in here. So 1 can be coupled with 3 and with 4. So let's put the pair 1, 3, 1, 4. 2 can be coupled with 3 and with 4. So let's put the pair 2, 3, 2, 4. And finally, 3 can be coupled with 3 and with 4. So let's take the pairs 3, 3, and 3, 4. So basically, we couple everything from A with everything from B. So it is like an x coordinate, this is a y coordinate, everything from A with everything from B. So in this case, hypothetically, A has 4 points and B has 2 points. So the intersection between the vertical lines through A and the horizontal lines through B is that 4 times 2 points. So number of elements of A cross B, with A and B are finite sets. Number of elements of A cross B is the number of elements of A normal product times the number of elements of B. There are also some extreme cases. For example 2, empty set multiplied with any set A is obviously empty set. Because there is nothing in empty set, so we cannot form any tail. Okay, so let's solve a problem that was a homework type problem, and which kind of combines calculations involving power set and Cartesian product. So let's put it on exercise 3. Exercise 3. The number of elements of A, let's say, is 3. Number of elements of B is 7. These are given. So let's find the number of elements in power set of A cross B. Power set of A cross B. So, how to do this problem? Let's look from the inside out. Power set of A here has 2 to the power 3 elements, so 8 elements here. B has, of course, it's a given, 7 elements. Cartesian product, we're going to say 8 elements and 7 elements is 8 times 7 is 56 elements. And finally, the power set of a set with 56 elements, it has 2 to the power 56 elements, it's a pretty big number. Okay. Okay, let's move on and discuss about functions. So let's sum A and B to sets. And A will be called the domain and B will be called the codomain. So a function f defined on A is very simple. There's a notation. A is called the domain of the function, domain, and B is called the codomain. It's actually a triple consisting of a domain, a codomain, and a rule which assigns to each element of A, assigns to each, very important keyword, assigns to each element X belonging to A unique, not an important, equally important word, a unique element Y, which is denoted by F of X, belonging to the codomain. So a function from A to B is a triple consisting of a domain, codomain, and a rule of assignment. The rule assigns to each element of A unique element of B. So this can be visually represented by a useful conceptual diagram. This would be A, domain. This would be B, codomain. A has a couple of points here, let's say a couple of points for A. B has other points here. So to each element of A, we associate a unique element of B. So we get, for example, this one, by an arrow, this one here. Nobody said we cannot target a previously targeted point, so we can do this two. We can do this one, and let's make it like this. It's a function from A to B. Function from A to B. To each element of A, we assign exactly one element of B. In other words, from each point of A, there exists exactly one arrow emerging towards B. So, from each point of A, there is exactly one arrow emerging towards B. It's very important to understand the concept. from each point of A, there is exactly one arrow emerging towards B. So, knowing this idea, conceptual understanding of functions, let's give some examples of entities which are not functions. Later we'll see that they are relations, but not functions. So what about this one? So this is not a function on the account that from this point of the domain, this is ABCD, there is no arrow emerging towards the codomain. So not a function on the account of this. There's a bug. Not a function because of this isolated point in the domain. There is no arrow emerging from the join. Also, another example of a not a function is this one. Okay, put something else, it doesn't matter now. So this is again not a function because in the previous example there were 0 arrows emerging from this point. In this example, because of there's a bug. There are 2 arrows emerging from this point, which makes it not a function. So a function is from each point of A, there is exactly one arrow emerging towards B. Okay. Let's discuss now composition of functions. So, best conceptual way to understand this is a diagram. Like if from A to B, there is a function f. From B to C, there is a function g. We can define a function which goes directly from A to C. So let's imagine f is like a program for which the input space is A and the space of all possible outputs is B. So the program f picks up an element x belonging to A, which is an input for this program, and operates and computes and produces an output f of x, which will be an element of the set of outputs for the first program. So f of x is the output of the program f, which is now could be taken as an input by the second program g. So g takes this input f of x and does a calculation of its own and produces g of that input, g of f of x, which is an element which belongs to the third set C. So the net effect is that we just started with the input x and produces an output, a composite output, g of f of x. This is exactly the composition denoted by g circle f, g composite f. So the notation is g composite f of x equals to g of f of x for every x is in A. An essential thing for a pair of two functions to be composable is the codomain of f equals to the domain of g. So that those two functions can be composed. Okay. Okay, so some special functions here a special function is identity function of a set A. Identity. So each set has its own identity function. A is a set. Define one sub A, identity function of a set A. Identity function of A defined simply by one sub A of x equals to x for every x in A. Why are identity functions important and useful? Because identity functions are as important as one, the element 1 under multiplication. One is an identity element under multiplication of real numbers. How can we express this one? Let's assume that do a similar diagram here. From A to B, we have a function f, and then from B to B, which can naturally follow by identity function on B. And the thing is that if I compose identity function with F, nothing changes here. So identity function of B composite F, 1 sub B compose circle F composite F equals to F. In this sense, identity function is identity element like a 1 for a number, but also it works in two directions. So if I have a function from A to B, let's put it here, then we can compose it to the left with identity function of A. And we get another useful relation. 1 sub A, sorry, F composed with 1 sub A equals to F. So 1 sub B composed with F is F, and F composed with 1 sub A is F for every function from A to B. Only in this setting is placed horizontally, and this setting is placed vertically. Okay, so this being said, let's move on to one-to-one functions. One-to-one functions. Simply, in very few words, one-to-one function, under a one-to-one function, different goes to different. But we'll let you explain better what it means. Different goes to different. So, a function f from A to B is one-to-one, one-one in the rotation, brick notation, if for ABX1 and ABX2 elements of A, if x1 not equal to x2, then f of x1 not equal to f of x2. So in other words, different arrows from emerging from the domain in the conceptual type of diagram, different arrows target different points. Different arrows target different points. So let's take an example. Okay, so it's a one-to-one function. This one, so different arrows target different points. So if x1 not equal to x2, f of x1 not equal to f of x2. Different arrows target different points. What is a defeater? Defeater, logically speaking, for one-to-one. It's a V shape, like as in two arrows targeting the same point. So whenever you see something like this, P is closed, this is not one-to-one. So like a defeater. It's a pattern that if we notice it, the function turns out to be not one-to-one, and if such a pattern doesn't exist, the function is one-to-one. But you see this V shape, not one-to-one. Okay, a nice example of one-to-one, identity function of a set A is one-to-one. Okay? Okay, so here is a nice theorem first. If the composition of one-to-one function is one-to-one, so let me try to prove it. The composition of one-to-one functions is one-to-one. So, in other words, let's we have from A to B, we have a function f, from B to C, we have a function g. This will be B circle f. F is one-to-one, G is one-to-one. So this is the givens. These are the givens, f being one-to-one and g being one-to-one. We want to prove that G composite F is one-to-one. To prove that G composite F is one-to-one, let's start with two elements in A which are given. Start with x1, x2 in A, x1 not equal to x2. So x1 and x2 are two different elements of A. Because F is 1 to 1, this F is 1 to 1, different also different under F. So F of x1 not equal to F of x2. So now we got two elements here. And first of all, we got x1 not equal to x2 in this set. And here in the second set, we got f of x1 not equal to f of x2 in the set B. So since f is 1 to 1, f of x1 not equal to f of x2, both of them, they belong to B. To those different elements, if we apply the function g, which is again 1 to 1, so since g is 1 to 1, g of this one is not equal to g of the second one, f of x2, on the account that f of x1 and f of x2 are not equal. And therefore, this can be rewritten as g spherical f, g composite f, f x1 not equal g composite f of x2. So let me see. We start with x1 not equal to x2. We get the conclusion g composite f of x1 not equal to g composite f of x2. And that's a reasoning that for any x1, x2, if x1 not equal to x2, then g composite f of x1 not equal to g composite f of x2. Therefore, after all of this, g composite f from A to C is 1 to 1. Okay, so this being said, so let's discuss a little bit the dual concept of 1 to 1, which are two functions. Let's define what is an unto function. A from A to B is unto E. In image-like terms, every element of the codomain is targeted by some arrow emerging from A. So if for every y in B, there is an x in A, such that f of x equals to 1. So in visual terms, using conceptual diagrams, every element of B is targeted by some arrow emerging from A. Is targeted by some arrow. So not only is a target, right? Is targeted by some arrow in this sense. Is a target. And to be just to be absolutely clear, is a target of some arrow emerging from A. So everything is taken. So this is A, this is B, for example. Everything is taken. Every element in B is a target of some arrow emerging from A. So in this picture, this function is unto, right? Because every element of B is targeted. And not 1 to 1 though. Because of the V shape, and it can be obviously seen. Right? So every element of B is a target, right? So let's give an example of a function is not unto. Not unto. Clearly, this is not unto, because this element is not a target. Still, it is 1 to 1 though, because there is no V shape. We cannot see any defleeter for 1 to 1. So 1 to 1. Okay, so what's the theorem which is similar to the one we proved for one-to-one functions? The composition of two onto functions is onto. The theorem. The composition of two onto functions is onto. Proof. So let's say the function a from a to b is onto, and from b to c the function g is onto. So we want to show that the composition G composed with F, G circle F, from A to C is onto. So what do we want to show? We want to show that every element, let's call it Z in C, is taken by some arrow emerging from A. So let Z belonging to C. Now, first, let's take it easy. Let's use the fact that G is onto. So since G is onto, we can select an element Y in B such that G of Y equals to Z. So there exists Y belonging to B such that G of Y equals to Z. So we got the Y here, this is Z in here. There is a Y in B, so that G of Y equals to Z, right? Okay, now let's complete on this Y in B. Y is in B, now because F is onto, so since F is onto, there exists an X belonging to A, there exists X belonging to A such that G of X equals to Y, because sorry, just F of X equals to Y. Since F is onto, there exists an X in A such F of X equals to Y. Since F is onto, so there is an X in A and F of X equals to Y. So via F, X is transformed into Y. So now, like in any composition, via G composed with F, let's cut the middleman, X is transformed directly into B. So what we got so far? Combining those two things, let's call this 1, let's call this 2, from 1 and 2, what do we get? G of Y, but Y is F of X, equals to Z. So in other words, G circle F of X equals to Z. So we prove the existence of an X in A such that under the composition it is transformed into Z. So basically we started with a Z, let Z be arbitrary in the set C. So any element of C is targeted by some arrow emerging from the set A. Therefore the composition is onto. Okay. Okay, now let's put together one-to-one and two. Let's discuss about bijective functions. So definition, bijective means one-to-one and onto. So let's see, what does it mean? Different arrows target different points and everything in B is taken. So in other words, let's try to visualize it. Take a visual example. Set A has elements 1, 2, 3, and set B has elements, let's say X, Y, and Z. Let's see, 1 goes to Y, 2 goes to z, let's say, and 3 goes to x. This function from a to b is a bijective function because it's one-to-one, different arrows target different points, and onto because everything in the codomain is taken. Another way to see bijective function is bijective function functions executed pairing or a matching or one-to-one correspondence in this sense. So all the elements of A are matched with all the elements of B one by one, right? So I like to see in this picture, right? Right. So the important thing is that the bijective functions are the most important thing about the bijective functions. These are the only functions with the following property. Bijective functions are the only functions with the following property. Reversing all the arrows from A to B, we get a function from B to A. Reversing all the arrows from A to B is a function from B to A, called the inverse function. Is a function F inverse from B. So the inverse function, if it exists, is a function obtained by reversing all the arrows pertaining to the function f from A to B. So it is the function f going from A to B, making different color here. If we reverse all the arrows, we get a function which is called inverse function from B to A. So the inverse function in conceptual diagram text is the function from obtained by reversing all the arrows from A to B, which will yield the function from B to A. So let's see. If f of 1 equals to y, f inverse of y, if we reverse the arrow, is 1. If f of 2 equals to z, f inverse of z, if we reverse the arrow, is 2. Right. And finally, if f of 3 equals to x, f inverse of x, reverse the arrow, is 3. So we can say f of 1 equals to y, equivalent f inverse of y equals to 1. F of 2 equals to z by reversing the arrows. In the case of a bijective function, f inverse of z equals to 2. And finally, f of 3 equals to x is equivalent with f inverse of x equals to 3. So the inverse function in this conceptual diagrammatic understanding is obtained by reversing the arrows of the function f, which yields a function from B to A. And this only can happen, this can only yield a function if the function from A to B is one-to-one and onto, in other words, bijective. So only bijective functions, that's why they are so special. It's a correspondence for which we can reverse the arrows and produce a function from B to A, which we call the inverse function of f. Okay, so a quick example, the identity function is invertible and the inverse of the identity is itself. Identity function from A to A is its own inverse. So from A to A, the identity function and identity function inverse, they are the same. Like in this case. Okay, so let's see. So in general, so in the course of this diagrammatic understanding, if x equals to, if f of x, this is an f arrow. How do I understand this? F of x equals to y is equivalent with reversing arrows, f inverse of y equals to x. I think the best way to understand f of x, we start with f of x equals to y. Treat this like an equation in x. So solve for x. We get x equals to f inverse, I put in red value better, x equals to f inverse of y, and there's the unique solution of the equation f of x equals to y. So the unique solution, in x of f of x equals to y. Okay, with this idea, let's solve the problem. Application of this idea. So let's try to do the problem here. So consider the following function. F, a function defined on to infinity, reducing 5 infinity, the intervals, with defined like this: f of x equals to x squared minus 4x plus 9. So let's show that prove that f is invertible and find the formula for the inverse function. Okay, so let's do it. Based on this idea, what we start with? We start from this, the most concise and quickest way to get the solution. To start with, f of x equals to 1, this equation. We aim to solve for x. What is this equation? X squared minus 4x plus 9 equals to 1. But be careful to put in all the specifications. X lives in a domain, y lives in the codomain of f. So x lives in the domain of f, so x is bigger than or equal to 2. And y lives in the codomain of f, so y is bigger than or equal to 5. Very important to write down those specifications. Now, we have to solve for x. Treat it like a equation of degree 2 and rewrite it as in the form ax squared plus bx plus c equals to 0. So x squared minus 4x plus 9 minus y equals to 0. So in this case, for a quadratic equation, a equals to 1, b equals to minus 4, c equals to 9 minus y. As in ax squared plus bx plus c equals to 0. Well, so if everything goes well, we'll have a unique solution in x. But we are facing a potential danger because who knows, maybe we have two solutions here or no solution. So we have to rule out those anomalies, potential anomalies. Right? So let's see, which are the rules? x1 comma 2 equals to minus b plus minus square root of b squared minus 4ac. For all of you who don't quite remember what that formula. So, which is 4 plus minus square root of 16 minus 4 times 1 times 9 minus y divided by 2, which is 4 plus minus square root of 16 minus 36 is minus 20, 4y minus 20 here, divided by 2, which is another one, x1, 2, one more time. How divide sum slash difference by 2? Divide every term by 2. How divide a radical by 2? Divide inside the radical by 4. So you get 2 plus minus square root of y minus 5. Now, those kind of things which I told you, you have to better write down the specifications at the beginning, they come in very handy at this moment. Because y being bigger than or equal to 5 ensures that the radical exists, because y minus 5 is a non-negative number, so you have no problem extracting the square root. So it's okay. So okay since y is bigger than or equal to 5. And this is very, very useful. But now, in y bigger than or equal to 5 guarantees that there is at least a solution. But we want to show that there is exactly one. So still, we have to choose between 2 plus or 2 minus. If both of them are true, then we are in trouble. But let's see. Use the other piece of information. X bigger than or equal to 2. Square root is always non-negative. So between 2 plus and 2 minus, we choose 2 plus on the account that x is bigger than or equal to 2. So choose the plus. Choose the plus means x is assumed to be bigger than or equal to 2. Therefore, x1 comma 2 is exactly actually a single x. So therefore, x equals to 2 plus square root of y minus 5. That's unique. Which proves that the function is invertible, right? So what's the formula for the inverse? Dominant of the inverse is a codominant of the function. Codominant of the inverse equals the dominant of the function, because we just switch, reverse the arrows. So H inverse defined on 5 infinity, inverse in 2 infinity. F inverse of, we can put F inverse of y equals to 2 plus square root of y minus 5, or the letter is, the notation is immaterial. We can just write just as well F inverse of x equals to 2 plus square root of x minus 5. So, like I said, notation is immaterial. You can put every letter, every symbol you want, right? You can put something like this. For every okay. Was kind of fast, but we need to cover all the materials. We didn't manage to cover all of it, but still, it's a decent approach to kind of coverage of material we did in the